Hi, everyone. So today we are presenting deep survival analysis for bankruptcy prediction. We're group 22. So the problem that we are solving is to predict bankruptcy. Given the current worldwide financial crisis, it is important for us to build a model that can actually predict bankruptcy within the time frame of 1 year or 2 year or 5 year or n years. So this is a typical partition of the dataset that we are working with. The full dataset contains more than 80,000 rows and 178 predictor variables for 80,000 companies. So as you can see, we have a F-year column on the very left, and then a few financial ratio features. And most importantly, we have this I bankrupt column at the very right, which is an indicator variable for bankruptcy status, with 0 signals not bankrupt and 1 signals bankrupt.
Before continuing to our data processing section, we want to first introduce you with some jargons. Horizon means that for horizon of T years refers to the time frame of future T years. Events refers to missing data or bankruptcy, and time to event is the years from now to the next observation of the event. Event indicator is the indicator for whether the next event is bankruptcy. And also bankruptcy within horizon indicator is the indicator for whether bankruptcy occurred in the horizon. So here's our training pipeline. For our pre-processing procedure, first of all, we generated labels of T, E, and H. H is calculated with horizon values 1, 2, and 5. Market data from dataset is also standardized. We use rolling mean and standard deviation as data augmentation method. It is also calculated respectively for each of the company. We choose the rolling window of 5, as data far in the past will have less effect on the bankruptcy in the future.
So we are now going to introduce survival analysis. This is a type of time to event analysis with a range of applications from healthcare, churn rate, to facility failure. The input are features, and the output is the probability of survival at any future time t. And deep survival analysis is essentially an extension of survival analysis, but using neural networks to model hazard function. The baseline experiment that we have in this project is built by binary classifiers, including logistic regression, random forest, and multi-layered perceptron. So we are now going to introduce the survival models that we are going to use in this project. So the Cox proportional hazards is a semi-parametric model, which is roughly a combination of baseline hazard function and logistic regression. And the hazard function refers to a function that quantifies probability of event at any timestamp t. The good thing about CPH is that it does not require specifying horizon, thus avoiding the censorship issue that we talked about earlier. And the deep Cox proportional hazards is an neural net extension of CPH, which utilizes hidden layers to approximate nonlinear relationships between covariates and hazard function.
There are also some more survival models. We also use random survival forest and most importantly, deep survival machine. As for deep survival machines, the input features X are passed through a deep multi-layer perceptron followed by a softmax over mixture size K. The probability of surviving time T for covariates X is then described as a mixture of K primitive distributions drawn from some prior distributions. Please note that apart from the learnable MLP weights, the parameters for survival distributions are also learnable. Given its relatively sophisticated architecture, it has the power to extract relevant features from high-dimensional data. As it can model multiple probability distributions, we can model groups with distinct survival probabilities. The MLP can also be replaced with a recurrent neural networks, so it can be used to model temporal dynamics of survival data. As for our model selection, we first use our evaluation metric of log loss. It is the loss between predicted probability of bankruptcy and ground truth value of H label. Then we chose our best models. This is the results for our binary classifiers. It can also be concluded from the graph that as the horizon increases, the performance of binary classifier decreases. It is intuitive that distant outcomes are harder to predict. As for our survival models, the result appears to be that the survival models outperformed by the binary classifiers. So here are our conclusions. Most of the models perform very well with a UZ of more than 0.85. Also, it's surprising to see that traditional machine learning methods produce comparable results. Also, survival models perform better in horizon values. and are capable of predicting the risk at any given future time.